most X-rays. So we're going to talk about rotating anode diagnostic X-ray tubes. All these concepts will hold true for stationary anode X-ray tubes, smaller tubes, lower power, used in dental systems, and a lot of the concepts will hold for CT in general, although there's a lot of variations in the CT world. I'm going to get into one of the very basic one. So this is the critical component in an X-ray tube. It's an insert. The inserts, these are glass. They can typically be made of glass or have metal components or metal ceramic components. But in these rotating anode tubes, these are the tubes that would go into a RAD system, a mobile system, a RF system, a small cath lab. Okay. So refer to the glass envelope. In the glass envelope, this is all in a vacuum. Okay. So we have what we refer to as a rotating anode. This is referred to as a target. This whole assembly is referred to as a rotating anode. These are bearings. Okay. And you have a cathode head. Okay. This is all the cathode. So one of the big challenges with X-ray tubes is because they're in a vacuum, okay, rotation, right? So this target is going to spin, but whatever the coating is on the ball bearings or whatever bearing you're using, when you put it together, that's what you got. Because you can't, in this kind of an X-ray tube, you can't lubricate. And this is one of the main end-of-life failures on the tube, and what happens. But so how this works, you have film. That's working. This happened at prison. And I went through this whole thing. All right. So you got to look pretty good. Okay, so you have filaments in a cathode. All right, so what I'm going to do, I brought some films out. So what I'm going to do, I'm going to pass around. This is actually X-ray tube insert. This was absolutely not a model functioning insert. It's been opened up, so it's not at the vacuum, so it's relatively safe. Should there be an accident and drop it, it's going to cut yourselves. It's possible, but it's pretty sturdy. It's not particularly dangerous. And so just pass it around. So you have a cathode head, and then you have filaments. You have an electrical field. So in the cathode side, you have up to negative 75 kV or 75,000 volts. At the anode end, you have positive 75 kV. What that creates is a tremendous energy potential. Okay? This is where the action is. This is why you need a vacuum in here, so that that energy potential can be controlled. So the filaments put a little power, low voltage to this cathode head, and the filaments bleed off some electrons. Because, and they create an electron beam. Because you have this tremendous energy potential, there's a tremendous amount of force when these electrons hit that rotating anode. And what comes out is an X-ray beam, but also comes out as 99.7% heat. Okay, so there are a number of challenges. One is what I refer to as the bearings and lubrication of the bearings. That's number one. Good quality bearings with very good lubrication. You need a very good vacuum in here so that beam comes out, and you need to manage your heat. Tremendous amount of heat. Now, why we use a rotating anode X-ray tube, okay, is because if this was a stationary anode and this didn't move, there'd be so much power going to this anode, okay, that it would actually heat through it. So these are made with tungsten, molybdenum, other alloys, okay, and in the higher heat units, they're backed with graphite. Control that heat to take that heat. But the key is, heat has to radiate out. If you get too much heat through this rotor, you melt your bearings. So this is a slightly different model. I have these different things. So we talked about the cathode head and the filaments. So this is a cathode head from the inside of an actual X-ray. You're welcome to take a look. So this is a bigger one. This is the last one was just called a 300 KHU tube. KHU refers to the heat storage in the anode. This one is, let's call it a million or a million point five KHU actually too. And the reason it is, it's got a much beefier anode, it's got graphite backs. Okay, this one is what we call metal center section. Okay. It's a different construction. The detail that you don't need to concern yourself with particularly is that the metal that goes to ground. And so there's the bleed off and extra tungsten from the filament is distributed evenly around that template. You'll see what happens when you don't have it in the slide. So in it we have the housing. Okay, that's cute. You know, Greg, there's two ways about the 80 pounds or 90 pounds of the model. Okay, but you can see the port. You can see where the receptacles. The difference between this is the horn angle. Okay, and that's what they look like. In this as well, okay, so what makes the spin is the stator. Stator is like a winding. Okay? This is what a stator looks like, and that's it. So how we make these X-ray tubes is we take that insert, all right, and we take it. First we take a housing, okay, either new metal, cast metal, or term metal, or we take a used one. If it's used, we clean it out, put it together with the insert, we put the stator in, we put the supporting components. We put a bellows in, which allows as the oil heats up, we also fill the oil, dielectric oil, insulated oil. And as the oil heats up, they expand. So we have a bellows in there to compensate for that expansion. You guys all get that? Yeah. To make it short, keep up. What's happening before they get up. So I said it was 99.7% heat. Okay, this is what a normal anode looks like. When we're building the inserts, okay, before it's sealed off, we actually get them over 10,000 degrees C. We get them hotter than this. It's not unusual for an insert to get to 10,000 degrees C in a high use site. Okay. So we have, these X-ray tubes, they kind of work on the edge of physics. You've got a tremendous amount of heat to manage. You got everything in a vacuum. CT is even much worse because you've got the combination of not just the rotating anode, but you've also got the entire tubes rotating targets. So this is the anode. This is our target. Okay, target assembly. This one is probably a 600 KHU because of the graphite back. This is the track. So this spins. This is where the electron beam hits. Because it's spinning, it makes an effective target area which is many, many times bigger than if it was just a stationary. Okay, and as it spins, of course, it cools and radiates heat. So that's a normal one. And here I have a normal anode. Okay, that's about a 400 KHU too. Yeah, every time. So I just need a lighter to that. So this is the cathode head. You look at one's going around. You have a large filament and a small filament. So the large filament is what bleeds off the electrons and creates the large focus spots. Small filament is what creates the small focus spots. And so everything I'm talking about, these are kind of parameters of the tube when you're buying an X-ray tube, where a system manufacturer is putting together systems, they need to understand. So in this anode, and the anode that we're passing around, you see that it has an angle. Okay, and there are different angles depending on your SID. Okay, so when the beam hits the target, depending on the angle, what creates the angle is beam. So depending on your SID, source to image distance, it depends on the angle and what you need. So if you have a small SID, you need a wider, bigger angle. And if you have a higher SID, you want a smaller angle. But also, a law, it's the inverse square law. So the distance, the dose of radiation is an inverse square of the distance. So if you double the distance, you quarter your dose. So it's very important to understand your SID in the system. Make sure that you get enough dose. Okay. One thing that when you're working with a system like LINAC or something you want to do, have a long SID, you have to have enough dose. You need to use a much bigger tube to get enough dose, high enough energy to produce enough dose to get it in.
The distance is long.
This distance? Yeah, because distance is longer. Distance is longer, and it's an inverse square. So, a couple things about diagnostic tube. This is not a promotion. I should have taken this IE out. IE is a manufacturer. But in general, these diagnostic X-ray tubes are the industry gold standard for those systems. Whether they use a new, as long as it has a new insert, okay, and even if it's a used housing and has used components, it's considered a new X-ray tube. Okay, there's no difference between a new X-ray tube that you would buy from your OEM and an X-ray tube that's reloaded, as long as it's been loaded with a new insert and with the components, the adequate components. Okay, so here people talk about reloads. Reloads are really kind of a misnomer. They are reused in the housing, but all manufacturers reuse housings. They all try to cut their costs and for the environmental impact. Okay, you've got inert metals, you've got steel, aluminum, lead. There's no point in not reusing them. So loading, reloading, and assembling are all the same thing. And the assembler is the manufacturer of record. So they're the ones that have to keep the track of the product under the guidelines of the FDA.
Is the oil reached too or no?
It can be. People.
Time for this, right?
So the oil, there's a few companies that do recondition the oil. Richard Harris over at our kid was one young actually started doing it, playing around with all parts of the car as a teenager. They pull the oil out, put it under a vacuum. The vacuum will pull any liquid out of the oil, run it through a filtration system. It's a crazy high filtration system. And also high heat vacuum filtration, and then they can put it back in the tubes. And it's darker, there's an uglier look to it, but it works.
So that's it. That would be considered as
That's the window. Yeah. So say it again, or
That's correct. You put oil here and you add that. When it is, you're actually breaking down oil and adding more acids and water.
now, okay, so you in every general sense, you're absolutely correct. Richard Harris would refurbish at Reliable Healthcare would refurbish tubes. You would use that process. There is a heating component to it. You don't want to overheat. You don't overheat the oil. So you're both correct.
But the moral of the story is oil is not that expensive.
Yeah.
And even when you get oil from the drum, you have to process it to increase dielectric strength. That's what we do. My family actually, my dad was the founder of North American Imaging. My dad was the local shooter for 35, 40 years. So to reprocess oil, to me, is a cheap way of processing. I mean, if you're not doing oil, I don't understand.
I don't disagree with anything you said. The only thing to say is for the environmental impact, anything that you want to reuse is a step in regulation. It's expensive. Right now, it's about $10 a gallon, dielectric oil, so it's not a big deal. certainly you wouldn't, if there was ever had a quality issue, you wouldn't want to reuse your oil. But in general, everything said here is correct in the general sense.
That's not bad. It's back to the some PCBs,
Yeah.
So,
So some of the things that go into it, and the other thing I'll say too is that CT is a whole nother level of different than what we're talking about here in diagnostics. The concepts are all going to be the same, but the amount of heat that you need to manage and the fact that the tube is spinning, so it has another gravitational force that's affecting it, creates a whole bunch of other issues. So an X-ray tube quality. So the reason X-ray tubes fail are bearings. They can be noisy and not necessarily fail, or noise can be a sign of regular failure. If you don't have a good enough vacuum inside the envelope, it can cause barking. Sometimes a new tube, they'll say you need to season it and get a few arcs out of it. By warming that tube up, you'll get the clean out the additional molecules in the vacuum and make it more stable. You can get tungsten deposits on the black envelope, which actually creates a shortcut for arcs. You can have a broken filament in the filament material. These are typically manufacturing problems. You can have this dielectric body of oil can create arcing, which is what we were just talking about the oil. You can have an oil leak or air intrusion. You get a bubble inside that tube arc. You can get the mechanical failure of sensors, number of sensors, pressure sensor, temperature sensor, depending on the architecture of the system, architecture of the tube. You can have a short in one of those, cause problems with your installation. Again, these are kind of these are assembly or manufacturing problems. Then you can have installation issues. The most common that we've seen are arcing in receptacles because the grease wasn't applied properly, grease really out of the oil in the receptacle applied properly. Or you can melt the filament because it didn't calibrate the voltage in the system. And that's not very honest. Yeah. It's kind of killing me here.
Hang out by your laptop.
Yeah, I'm gonna have to do that.
put Roger on it. Roger can hit the button for you.
Yeah,
All right.
just say next slide.
He just showed it where.
So we're done for you.
Yep, just you hit the button, show them what button to hit.
We're getting a preview of my slides anyway.
You can't.
Okay. So this is an example of an anode that is kind of pretty drastic case. Here's another couple anodes that have the same problem. Passing around. So what happened here was the tube was probably cold with high power. It's the kind of thing that can happen in a trauma case where you've got a system that's sitting there, the tube's cold, all of a sudden you want to go up, you have a big body, you need to x-ray real fast, and then boom, you hit it cold, pull it out of this. This is
Wouldn't it be the part of the process,
pardon me?
Wouldn't that be part of the process to form the tube?
You're absolutely right. In our corporate world, we warm up the tube every single time.
Yeah.
But
But
realistically, in real world, I mean, that's the way you teach it, that's the way you're supposed to do it.
Yeah.
But in the real world, when you have that trauma come in and that corporate role, the provider may not give you the time you're supposed to have to.
Yeah.
Once you're there, to warm up your tube enough, you're not gonna warm it up where you park because you don't know where you're, how much time you're actually gonna have, you gotta warm it up outside. I can warm it up in an apartment before I drive back to the ER. I may have to wait 35 minutes before I can actually get in there. Or he wants to shoot it, now, get a shot, because someone's bleeding out on the table, good head.
Right, so what can happen is that over time, you can get craving on the insert. So this is tungsten that's built up around the core from the target, from the filament. What happens is this creates a path of arcing in the tube. So this will kill your tube. So these are obviously end of life. Okay, the other thing that can happen is filaments can die two ways. So if you put too much voltage on a filament, and it often happens to the small, because they're trying to get high resolution, a lot of power to the small, it can be melted. So you get a tube back under warranty and you see this is a melted film. Okay, this was too much power. The other problem that you can have is you can have intergranulation in filaments. And that's where the filament just kind of cracks. And it has to do with some material failure in the tiny tungsten filaments. And so it cracks, and that's a manufacturing defection too. Okay, now let's see if this will work. So just to give you an idea, concentrate, watch for a second. This is what arcing looks like in the tube. Can you see that?
Oh, yeah.
Okay. So, and that's what now, it may not kill the tube, but it certainly is hurting its feelings.
Scaring the patient.
And scaring the patient, yeah. And that's the kind of thing, if it doesn't kill the tube, that's the kind of thing now we want to do is you want to go and season that tube. You want to take it from a very little at a time, a little bit of power, to a little power, step it up and season it. And if it has what's called a getter in it, the getter actually can isolate any contaminants that are in that vacuum. Okay, so in the installation, there's a calibration. And so a product data sheet comes with the tube, and you have anode and heating and cooling curves, and you also have the filament. And so it's important that the engineer note these and make sure that he adjusts he calibrates the system. A lot of systems now have automatic calibration, so you put the tube in as long as the tube is compatible. It will assume these curves and run through the calibration itself and define the curves. And the other thing, in another system, you can be a tube library of generator. So, for instance, in a CPI generator, there might be 100 different tubes that you can use in that system, and you go into the library and get the correct tube. The other thing that it tells you about is the state of things. I'll get into that in a second. I told you to. Yeah. And have to. So the characteristics you need in the tube, particularly if you're looking at a compatible tube as opposed to buying from the OEM, the OEM original compatible housing. That has to do with the mounting the typical typical examples of Annex 100, one of the most common tubes in our market. You have a horn angle, which is the angle between the port and the receptacles, so that when you install it, it's pointed correctly in the cable. You have the stator type, and the stator type is typically measured in ohms. There's probably half a dozen common stators, and you want to have the stator so that you have the anode spinning at the correct speed. The insert, so you want the target. Biggest thing is the size. So we generally talk about 3-inch and 4-inch targets. That's different ones around. Here's a 3-inch target. You have the angle, which is one that determines beam coverage. Most common is 12 degrees. The heat storage in these rotating anode X-ray tubes, they're typically between 150 KHU, which stands for kilo heat units, and 810 KHU, kilo heat units. Talk about CT, we talk about heat storage in MHU, or million heat units, for the manufacturers of units. Local spot size, very important, contributes to the resolution. US, mostly we use 0.6, 1.2. In Europe, for instance, it's mostly 0.61. And then you talk about the KW, refers to how much power you put to that, to each track. How much power the cable was measured. So these are the things that you're looking for when you compare two tubes. These are kind of the aspects that you're looking for. So we mentioned horn angle. So this is the chart of the horn angles. Most common is usually 90, but you can have any of these on a system. Some of the European manufacturers, particularly like CGR, France, use different ones in history. But the most common are 90 and 180. You can get a 270 or a 270, which referred to as a 270 reverse. So the original common models in the market, these are common manufacturers. The original tubes can be made by the OEM, GE, Siemens, Philips, to a certain extent Shimadzu, make their own extra tubes, or they can be bought from an independent manufacturer, which is a Barrix, IAE, which is an Italian manufacturer, Canon, which was Toshiba, Kailan. So you can put the original tube on, which is the same tube, same insert, same housing, everything's the same. You'll choose the tube in the software. You can put in a compatible tube. So it's usually the same housing, and it's a tube with all those parameters that we discussed the same. The fit should be identical, and the function should be equivalent. Sometimes you need to do a little bit more calibration. These I'm going to go through pretty quickly. These are just some pretty common models we see in the marketplace. X100 and GE, their workhorse, they've been using on their systems for years and years and years. The OR3, which is the C-arm tube for the OEC 9800, became GE. Philips, very common Philips models. They're usually referred to the SRO 3300 or SRO 550. More common is the 3300. Bearing medical systems or Barrix. These are very common diagnostic tubes, somewhat generic in their housings. You'll find these on a lot of systems. Shimadzu, more and more Shimadzu systems in the marketplace. The rad speed or the portable. Siemens are almost all 600 kHu, and they all use this Opti 100, 150 housing for diagnostic tubes. And they get cath lab tubes, different, but for most of the diagnostic tubes, they're using an Opti 150, or they refer to it as an Opti, it's really the same. Carrier and Canon and Toshiba electron products, these are common models. It's interesting that they're seeing more and more of the portable systems with these Canon tubes. For years, the AMX4 and 4 Plus were the workhorses of the industry. Now we're seeing a lot more of these smaller portables with these tubes. With the mobiles too, with these, it's a very similar housing, it's a very similar insert. It's a different stator, low impedance stator. So it's one of the details when you're buying these tubes when you doesn't understand.
They last forever, so we've got some doctors that were chiropractors.
Well, it's great about that. People say, okay, how long will this tube last?
Doesn't know.
But how long will your engine last in your car? Okay, well, it depends on a couple of things. If you're a sales guy, right, and you're driving all over the East Coast, and you get in your car, you drive 1,000 miles, and you're driving a nice even 60, 70 miles an hour, right, and you hardly stop, your car, that engine's going to last for 250 or 500,000 miles. if, you keep your car outside, jump in your car, you turn it on, you immediately race to the market and turn it off, and you get out and race right back home, your car's gonna last a lot less. X-ray tube is very similar. If you take an X-ray tube, the worst thing is an X-ray tube that goes from cold right to high use. And sometimes low use tubes are the ones that die the soonest for that reason. Okay, a tube that you turn on and runs all day long and is nice consistent heat will last the longest.
How long is too long to sit on the shelf? If you bought a tube, then sit on the shelf.
The standard is 6 months. That being said, you can go years. You literally can go a couple of years. What you want to do is have it to the store on the shelf for a while. You want to very carefully season it when you put it in. You want to go through an extra long seasoning process. From a very, very rapid breakdown. What that does, there's no perfect, in the universe, there's no perfect vacuum. So inside that envelope, as that vacuum degrades over time, what you're doing is you're cleaning up the vacuum by going to one. You get some arcs, you get small arcs instead of those major arcs we saw in the video, but they will clean up. But in general, like as a manufacturer, you wouldn't want your tube to sit on the shelf longer than 6 months without being either retested or seasoned. So I'm going to kind of feel here. A little ahead of time, I got to give you guys an hour so you get your credits and fees. So I'm going to get into this is CT technology here, right? And it's not really the only technology about CT I'm going to talk about. It's anode and ground. So in a conventional X-ray tube, you have what I've explained so far. You have a cathode head, you have an anode, you have a reaction. But when the electrons hit this target, some percentage of them, about 30%, bounce. And when they bounce, they also produce radiation, a small amount of radiation. Okay, but it's considered soft radiation. Okay, what gives you a good, clear image is a hard beam. Okay. So this softens the beam, or it adds kind of fog to the image when you have rebounding electrons. So the architecture that they came up with is anode and ground. So in anode and ground technology, two things happen. Instead of being 75 kV negative 75 kV positive, you have 150 kV negative to ground. What that, because it goes to ground, what that allows you to do is add an aperture. What this aperture does is this captures the underlying electrons. Okay. What that does is that effectively takes 30% of heat away at the source, because that's the 30% of the electrons that rebound. What it also does is it takes out a lot of the soft, takes out some of the fog out. This is not any way implying this is something to add to an X-ray tube. This is all about the architecture. But, you talk about AEG or anode and ground technology for CT tubes, this is what we're talking about. There are also some diagnostic tubes that are coming to market. So one of the key factors in this is that they run cooler. And one of the reasons they run cooler is they put active cooling in these channels. Okay, so that you're actually cooling, pulling heat out of this anode right at the source. Heat generation. Well, if I can't get this going long enough, I'll just run these slides like this, and then I'll eat up a lot of time. Okay, so how this fits into the architecture of the tube, this is what an anode and ground tube looks like diagram. So you've got negative 150 kV, 2 ground. Again, you've got your spinning anode, techniques to cool the anode because you've got so much energy going. And this is that aperture. Okay, so the heat, the rebounding electrons are caught here, and this has active cooling to these channels. It's one of the first new architectures for X-ray tubes from the time that Runkin and whoever else identified X-rays and how you make them. The architecture really had not changed very much. And they started rotating the anode to get more surface area, but overall it was kind of the same concept. This is one of the first changes in architecture. And now some of the advances, not advances in this, there are some other advances now in CT technology. So I talked about off-focal radiation. I'm sorry this is so blurry, but so in a typical glass tube, you might get over 20% rebounding electrons, soft beam or soft X-rays. That metal center tube that I showed you, because that metal is it does capture some of the off-focal radiation, some of the electrons, so it does minimize some of the off-focal radiation. But anode and grounded will get you something around 5% off-focal radiation, so it's much clearer than it.
Okay, those are labels.
Yeah, those are labels, and the only reason I have them is just to show you what. And these are labels. So, you know, when you're trying to buy a tube, this is the information your technician has to from the label. I mean, it tells us a lot about it. It tells us the focal spots. Typically, the part number, the model number, will give somebody who's supplying a tube everything. Interesting sometimes. The ages of the X-ray tubes. I mean, I've seen X-ray tubes come back 30 years old, particularly in a low-use rad system or even a high-use rad system. It's treated properly. So that's all I have for slides. Questions? Comments? Yeah.
You mentioned,
Okay.
you mentioned about the coolant. So the coolant is encased in the housing, or is it like a circulating outside gets cooled off and then comes back?
Okay, both. So okay, all this area is filled with dielectric oil. Okay. In the smaller tubes, that's why okay, the heat radiates from the tube into the oil to the housing. You're not putting that much energy into it. When you get to a million heated tube, typically you have a heat exchange. So you have tubing connected to this, and it'll go to what's usually used as oil to air heat exchange. It can also be this can also be work. So you have the oil actually being pumped through the heat exchange. In CT, you always have a heat exchange because there's so much more heat. Lars?
I'd just like to mention, like, when you talk about anode grounded CTs or being anode grounded system, the oil is for a different application, right? Some typical X-ray tubes, right? Oil acts as an insulator against the housing of the ground, right? So that's why that dielectric strength is very important. This is the whole point of processing oil. When you have an anode grounded, it's for cooling purpose, not for insulation. You can actually have air inside of your tube without having arcing. This is why you get those artifacts and mostly the GECTs, right? Because you can get air trapped in there and it's not a big deal. But when you talk about like seamless CT, it acts as both, not just for cooling, but as an insulator. And that's why that dielectric strength is a big problem, right? So that's like the difference between like reprocessing used oil or using, you know, new oil, right? Because that dielectric strength has such a big purpose, especially with diagnostic tubes. Obviously, it's sealed, it uses it against insulator, against your housing. So if you have low dielectric strength or you just use oil out of a barrel, that's going to break down quicker and you're going to have arcing to the housing versus, again, the anode ground. You're directly onto the insert itself. When they put that high voltage cable in there, you go right into the insert. That's why that technology is so sophisticated compared to your typical rotating or your typical diagnostic tube, right? So I just want to keep that in mind. Like, this is how all these different factors play into, you know, the lifespan of your tube, right?
Yeah, and that's absolutely right. And underground too, because it goes to ground, you don't need the dielectric aspects of the oil. It's really just, and a lot of sometimes, for instance, the cannon tubes, they don't actually want to use glycol. They use glycol. Right? More questions?
Yeah, I have a question.
Sure.
On one of the anodes, I saw evenly spaced dashes or something. Is that normal?
No, absolutely not. Glad you brought that up. So what's happening there, you know, as the correct, so that's what a normal anode should look like. This is an anode really just after testing in the back. And that's what you want your anode to look like. This anode, this is what we call a mud flap. Okay? And this is a tube that's had too much power for a while. Okay? And then eventually they hit it cold and it cracked. The one you saw that has the, one of them that went around has one spot in there. The other ones has it. What's typically happening there is either the stator is dying, has a short, or the bearing's going. And so that anode stopped and then kept going. As it stops, you know, because it's getting so much energy, it melted there, the target melted in the spot. Okay? And so, like a lot of this one, manufacturer gets it too back, and they say, hey, it was your, check your stator drive, check your rotor board. That's what they're talking about, because they've seen that. And they say, okay, you didn't calibrate the filament voltage. And what they're looking at is whether the filament melted or whether it was a sharp crack. Sharp crack means it was a material failure. If it melted, that means it was too much voltage. Other questions?
Are you using any other material besides copper?
Well, so for nanotubes, they'll use a little bit somewhat different material. They'll use tungsten, and other tubes will use moly. A lot of them are alloys. Yeah, so you get moly, molybdenum, and rhodium, and tungsten. That was common. Yeah. No other questions about X-rays?
Have you seen targets hit due to improper operation or improper tube setup or rotor speed? So it caused hitting grooves and stuff there?
Yes, yeah, all those things.
Yeah.
Yeah, and that's, so the stator has a certain resistance, determines the speed. One thing I didn't mention is that you have low speed tubes and high speed tubes. Low speed tube spins at 3,000 RPM. High speed tube spins at 10,000 RPM. A little bit of variation there. I think hertz is your 50 hertz is a little bit different, but generally that's how it is. Some CT tubes spin at one, but if you're you're putting high speed power through the tube and it's actually hooked up to low speed and not running that speed, you'll get damage to it. And you can get that fitting anytime that stator is not running right, or your rotor board's going, or you have a short stator, or bearing is going. It's all about the speed. Yeah, speed and about the cooling.
Sometimes they'll run for years if you have a guy that installs it properly with the wrong rotor speed, it will wear off prematurely.
Oh, yeah.
And you don't even find it when you're flying around looking inside somebody's machine. Sorry,
there's even ways when you send it in to the manufacturer, because whenever somebody returns the tube within the warranty, always go to like the manufacturer to check it out. You can see things like sink filaments, right? And right away, you don't know if it's a manufacturing defect or an installation or, trigger, is what we call it. Most people don't like when you send them the evidence of, yeah, somebody messed up and, you have to send filament and, this is on you, you know?
And sometimes it can be a little bit confusing.
Right.
Back to the filament. So sometimes what you can have is you'll have a filament that isn't set properly, and it'll be an intermittent problem where it'll ground to the cup. And then it'll do all kinds of very funky, give you very funky results, because sometimes it'll work, sometimes it'll get hot, it'll get hot, and then go to the cup. You won't get a good image. There are a few things in there that are, you really have to examine and figure out what the problem is.
I'm always amazed that it doesn't ground to the cup more often, because as tight as those specs are and as hot as that tungsten gets, and you get that slack to it. It just amazes me that it works, so well.
Yeah. Well, these diagnostic tubes, I mean, it's amazing that they work. But when you get into CT, most amazing thing are the amount of Gs you get on. So now the holy grail right now in CT is 0.2 second rotation. So what that means is that this tube is more or less the size of a 33-gallon tank of oil, okay, for weight and for size, for mass. Is spinning 5 times a second around the patient. Okay, when you get there, you're talking about 40 Gs. Okay, you got that's everything has to stay in place to make that tube work. I mean, the architecture, the geometry has to stay. You can't have a cathode bending, you can't have your anode moving, and tremendous amount of force because of it. So CT, and by the way, no one's gotten to 0.2 seconds. A few people have claimed to, but no one's gotten to 0.2 yet. 0.25 is about the fastest spinning rotation. And if you have a system that'll do 0.25, you don't want to do it unless you really need it. You want to use a slower rotation because you're really at the edge of physics when you get that hybridization. Everything else is fine.
Better have that thing shim properly and waiting for it.
Yeah.
It needs to be balanced. I mean, there's a ton that goes
Yeah.
into it. I have a Siemens strap C at my booth. So if you guys want to come check it out, so you can see the open side of the CT.
And I will say about those Stratons, I mean, I've never really worked with the Straton technology, and so I really didn't understand it. Jeff explained it to me finally. It clicked with me exactly how that thing works, and that is a whole different geometry and a whole different thing. It is very weird too. But I finally had the breakthrough yesterday.
You have to visualize it, you have to see it, and then it all kind of comes together. You're like, holy shit, these Germans.
It is.
Yeah.
And the technology stayed more or less the same as when it was discovered. I won't say invented. Invent some array. But the technology stayed conceptually the same. And so, really until the late 90s, they started perfecting some of these other things. The other thing about CT that I'll say is that now what they talk about liquid metal bearings, not just in CT, also sometimes in cath lab. And that's a big breakthrough because of the fact that they need to be down because you can't lubricate them. So at least a liquid metal bearing will last longer in many cases, run smoother. But it also, different bearings are different kinds, and they are not created equal. Different bearings. There's some bearings that, and I won't go into details of manufacturing names, but some bearings, when you stop them, they're taking a little piece of that bearing out. So other ones they perfected.
They don't want anything to last forever, right? Because they don't have a reason to make more.
The AMX tube, it has 1970s
How long an extra tube?
1970s tube, and the state inspector came out and she said, there's no way it's going to pass. And I said, trust me, I just tested
What kind of system?
Was an AMX tube. Yeah, and it passed, and it was within 2 months it finally died, and what died was the stator. Yeah, the tube was still good, the stator stopped spinning, so you couldn't get above 50 kV because it just wouldn't put out that energy on it.
You know what they say, right? Extra tube manufacturers, they want it to last 12 months and 1 day.
Yeah.
This is not an advertisement, but there is somebody that wants to say it too for the last 24 months.
Yeah, that would be nice. You know, you gotta understand though too, like in the manufacturing process, I have a uncle that works at American Tube Division, he works on the sector side, but I've done a couple tours there. We have a long history. Some of the technology there is amazing. You just start to understand that every tube is different, right? The way it's manufactured, the alloys, everything. I mean, they're all similar, but all different at the same time. And sometimes you get tubes that are made perfect, right? That last 30 years. And some you get 12 months when they
Well, that's really true. Like from the tech point of view, you learn real quick, even when you have brand, they just replace both your tubes, your fuel tubes.
Yeah.
They tell you it's the same tube, the same manufacturer tube. And I guarantee you, one will shoot better than the other. Every single time.
So-
And you learn real quick which group you want to use.
So one actually shoot better, you're gonna have to see that clinically, huh?
Yes, you can see the 30% difference between.
An image quality.
And it's not a difference between the two generators?
Well, and it could be the generator,
Right.
but.
It's like AMX 4s.
But all
I can
things
tell
being
it-
equal, we know they didn't change the generators in the
Yeah.
room, we know they changed
Yeah.
the tubes.
It's like the AMX 4s, I can tell the difference on my radiation meter between a unit that was made in China and the older units. And the older units had a better KV waveform.
It's what's made up in the filaments and the emissions, right? And you can start getting into like nitty-gritty, but based on what we've seen, I mean, actually, my company started loading the Toshiba product line back in the day, and that was one of the biggest issues versus the variant at the time was they couldn't get the alloys correctly on the filaments, so their emissions were not correct. Variant actually has a very high rate emission output, and it must be really good material for the filaments versus what Toshiba. It took them a long time, it took them a couple of years to get in from again to having equipment tubes. Again, there's also other things too, I mean, like you were saying, and they were saying about, the longevity of the tube, tube warm-ups, like, doing proper PMs, all that kind of stuff. I mean, we're service engineers, that most people are, and I don't want to tell you how many rat rooms and art rooms I've been in that have just been neglected, and you're like, well, are you really that, when you pull a cable out, there's no reason to flak inside, are you really that, like, surprised that the tube blew up? I mean, some of it's like, oh, you're common sense.
And the answer, if you have 1.2, 0.6 volts, there's in it happens, and it can meet that. So you have 0.6, it's not exactly every time you manufacture.
Well, it's an interesting point. Now, the IEC spec for that, which is 60633, if I'm not mistaken, actually, the point you can have 50% variation.
Oh, wow.
So, yeah, so the 0.6 can be up to 0.9.
That's huge.
So you could have a
One
difference.
point
Yeah, and I can see,
You're gonna have a different.
yeah, because we can see visually a 30% change.
Right.
That's just the standard, that's why.
I bet you're right.
That's,
Yeah.
and they see a visual difference.
And that one line clear phantom on it, you see a difference in the line clear phantom and all that too.
Oh, yeah, you're gonna lose. Get smaller.
Yeah.
So,
For sure.
0.6 to 0.9.
50%.
Sharper.
Yes.
All right.
So your spec is like, it's at 50%. Yeah, you're over 0.6, but.
So you can be 0.3, you could be 0.9.
Yeah, every day it's made different, man,
And some of the, but, I disagree with that a little bit, but, some manufacturers have much tighter tolerances.
Yeah.
And part of it has to do with the amount of automation fast.
Well,
If you have an automated process, your body is much more consistent. Right. Than if if everything is done by hand. So some manufacturers that haven't invested in their manufacturing capabilities are still doing things, and they kind of count on tribal knowledge, which is great until the 2020s when there's a lot of turnover in the factory and there's a lot of problems in the factory. And then people that were doing it for 20 years are no longer there. You have somebody who's trying to read work instructions that are inadequate and get a variation of quality.
I had great success with one manufacturer. I would be testing the filaments, and their filaments were relatively consistent within 50, 20% of them. And then I had other manufacturers,
what, that's all correct, depending where, what manufacturers use it. And they tighten their spec, their specs in the film, say, why are we doing 50, even though it says 50, we're gonna do 15, we're trying to keep it at that quality control, which is true. And we might spend a little more money for that instrument, but
You need that leeway.
It definitely, I think the manufacturing is better and better every year, where they start eliminating some problems and tighten your tolerances. I mean, that's just how the way it's
The way the world-
right, but.
The way the world should be.
Right, it's getting better and better. And there's definitely things that are funny though, because like, like back when we were going, bearing versus, Shiba, right? You would notice certain things, like all of a sudden you get a batch of like MS100 inserts that, which is Shiba, that are super noisy, like screaming. You're just like, no, send all of that, it's not, it's not that does manufacturing, and getting into that. That's some of the things in your quality control, right? You have to go through all that, you have to go through all the testing, you have to go through the places. Again, all this supposed to be service engineers. It takes a little bit of time to change out a tube and go through all that. And the worst is when you get it on there and you're like, this is a big tube and it's streaming right now. Perfect.
Yeah, you'll have a pissed off customer.
And did all that work. You can-
Right.
Some manufacturers the tubes are just noisier, just by their nature. So I can tell you one story from the industry. I used to work for Varex, and we made the original Variant Medical Systems, made the original OBC 9000 tube, Rad 99. But GE wanted to lower their costs, as all these manufacturers do. They started making it in Bangalore, India, and the tube would work. Finally, they got the tube to work. But once it did, the doctors that were used to a relatively quiet Varex tube, when they got the new tube that was noisier, they all complained. And so for years, they had to come by some percentage of Varex tubes just to satisfy those doctors that had been used to it.
Sure.
The other thing that will happen is, might not be noisier in terms of dB level, but there's quality signals. So you'll get some that'll sound like, and it sounds like a garbage disposal, right? And it can be objectionable, even though it might not be loud. It's just a nastier sound. Harsh sound.
And I think too, one thing to look at is going to the manufacturing side. Might be really loud this way, and then you turn to 290 and with no noise.
And that's another thing, where that happens, and particularly at the portals. If the manufacturer spec doesn't require them to test for noise, first of all, test for the noise. Number two, test it at different orientations.
Right.
You can find that.
Yeah.
Yeah.
And that's why I piss off chiropractors, because when I go into a chiropractic site, they're always facing the wall. Right. I need to test it with my meter. I pointed at the floor. That tube hasn't pointed at the floor. Who knows how many times?
Yeah.
And it makes it to get noise involved.
And in the bearing, and you have a bearing race, okay, a track where the balls run, okay? And if you're running it always in the same orientation, it's eating into that race in a certain orientation.
Right.
And when you do move it, then it's moving that race, and it creates that difference.
I got really mad at her. When they changed their.
So did I.
And they went, I like it. I got mad because I got, when they went to their ion tube bear. Why did you harden the bear? And that's what they did for longevity, right? And cut loss.
Well, there's typically two coatings that they use in bearings, lead or silver. Lead is softer, typically quieter. Lead deforms easier. Silver is harder, it's louder, and it doesn't deform. It can last longer depending on the application. Particularly if it's more stress on the bearing, it can last longer. Typically, it's louder.
I got really mad. I said, when you read your tube went from nice and quiet, and all of a sudden, it's not a bad noise, just a different. And, you hear this nice quiet, and go, okay, why did that? And I almost felt it, but people that are sitting in an X-ray is very different. They get that perception. I say, it's him.
Yeah.
But I can go back and I said, well, take it or leave it. I got to pay it. I don't my business.
Right.
Other questions?
Just gonna say, if anyone works on OECs, do not over-tighten that damn high voltage connection on those things. We had a customer that bought a GE OEC from GE, reefer, gold seal, and they had a bad high voltage cable because GE didn't replace, well, GE doesn't do the refurb, somebody else did it, but they didn't replace the high voltage cable, they just painted the unit, spray and pray. So I replaced the high voltage cable, and thank God the customer was in the room when I pulled out the connector, because you heard boom, 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 because the oil's coming out of the tube. And so I know what probably happened was they probably had a blown tube on that unit, they got traded in to go up to a 9900 or something, and they replaced the tube, cranked it in there until they cracked that plastic on that well. But of course, that rubber conical plug filled it, and I have a picture of it, you could see on the rubber where it had a seam where it filled that gap. But
And see, you went and broke that too.
yeah, and they wouldn't blame you.
That's the story.
Nice and easy. And time a little turn.
Yeah.
That's all you need.
That's all you need. Yeah. No Hercules.
I do want to tell you guys, my intention here was X-ray tube 101, and then I got this crowd.
Hey, we just want to see, and I love it. This was good presentation. You put your contact.
Yeah, and well, tag parts up here. So since we're all being friends, okay, I'll give you a little personal background. So I had my own business. I was a dealer for what was then NRA and then became Varian. First RSNA was 1989. I love selling tubes. One day a guy in Park got a tube, I didn't know what an X-ray tube was. Found out it was worth $20,000. I fell in love with it too. So, and then the situation, the economic climate changed for me, and I got, they asked me to come in and come inside work for the manufacturer. So I've been the sales manager for Barracks, global sales manager for the aftermarket, or the sales manager for the Americas. So, that was so recent. Yeah. And now, Barracks and parted ways. Now I'm a distributor for Italian manufacturer, IAE. That's why some of these I took out and tried to sanitize this and missed IAE a couple of places. This is not meant to be a plug, commercial plug, it's really the education. But to give you some background on education. And if you catch me alone, I'll say, who I was referring to when I said such and such a thing, who I was referring to when I said something else. I can tell you all about it. But that's my personal background. I live and breathe this technology, and I enjoy talking about it.